differential equations, type 2 real world, C, acceleration in a vertical direction. In 1995, we have a particle of mass m falling from rest, and it's falling against an air resistance of mkv, where k is constant and v is the speed. And we have to prove that the time taken to acquire a speed of g over 2k is given by natural log of 2k. Okay, so again, let's have a look at what's happening here. So we have a particle that is falling from rest. And therefore, if it's falling, it's going to have a downward force due to gravity. So in other words, it's going to have its weight. And then it's going to have air resistance acting on it in the opposite direction, which is given to us. So let's see what we have. Well, we know that the mass is given to us as m. We're not given any units here in this question. So it's starting from rest. So its initial velocity is going to be 0. Therefore, its starting point is 0, and the time at the start will also be 0. And the resistance then is given to us as mkv. And again, no units given there, so not given to us in terms of newtons or kilonewtons or anything, okay? So what do we know? Well, we know that if we have the particle falling, it's accelerating in a downward direction. Therefore, if we look at our net forces, what are we going to have? Well, we're going to have downward direction, so leading force will be weight, opposing force will be resistance, equals mass times acceleration. The weight is going to be mass times gravity. The resistance, we're told, is mkv, the mass m, and a, the acceleration. So, of course, if I divide everything across there by the mass, well, that leaves me with an equation for the acceleration is equal to g minus kv. Okay, so if I now look at my start and my end limits, I can then decide how I'm going to use my acceleration formula. So at the start, I know that the velocity is 0, starting from rest, and the time is 0. Whereas at the end, the velocity, we're told, is g over 2k. And I need to prove that the time, if I go back, I need to prove that the time is going to be given by natural log of 2 over k. So I can't use that, I have to get that because it says prove. Okay, so that's what I want in the end for my limit. So I'm trying to find one of my limits. So therefore, if I'm looking at v and t, I'm going to say acceleration is the rate of change of velocity with respect to time, in other words dv dt. And if I rearrange that equation, I'm going to get 1 over g minus kv dv is equal to dt. And then my upper limit is g over 2k, lower limit is 0, upper limit is t, lower limit is 0. So if I integrate 1 over g minus kv, well, that's 1 over a linear function. And if we have a constant over a linear function, when I integrate, it's natural log of the denominator divided by the denominator differentiated. So if I divide by g minus kv differentiated, well, if I differentiate g minus kv, I get minus 1 over k. So I'm going to multiply that by the natural log. And then my upper limit is g over 2k, and my lower limit is 0. If I integrate dt there with respect to t, well, I'm just going to get t. So in other words, I'm integrating 1 with respect to t. And now if I sub in my limits, it's upper limits minus lower limits. So if I sub in for 0, I'm just going to get g minus 0, and then that's going to equal t. Okay, so let's simplify here. We have minus 1 over k natural log g minus, well, k is going to go into k, leaving me with minus g over 2. And then that's minus minus, so plus 1 over k. Natural log of g is equal to t. So that is going to be 1 over k natural log of g minus 1 over k natural log of g over 2. And of course, I know by my log rules, which is page 21, that again, if I have a log minus a log, then I just divide once the bases are the same, obviously. Okay, so let's tidy that up. So therefore that gives me t is equal to, well, 1 over k is common, and then I have natural log of g divided by g over 2. And if I divide by a fraction, I turn it upside down and multiply. In other words, my g's are cancelled and I'm left with natural log of 2 times 1 over k, which is natural log over k, which is what they wanted us to show. Okay, so the next part then, part 2, is to is to prove that the speed of the limit, the speed of the particle, tends to a limit of g over k. All right, so if I need to do that, I need to go back a step here. So if you're the type of person that always integrates and works out what your constant of integration is, then you already have an equation now for t in terms of v. But if not, and you've done it the way I have, then we just need to backtrack a little bit up here and say, well, what would this equation look like up here if I didn't know what my end speed was? In other words, if it was just v. So in other words, this limit here is going to be v, but all the other limits are going to be the same. Well, what does that leave me with? Let's see. That would leave me with minus 1 over k natural log of g minus kv at the limits of v and 0 is equal to t and 0. Okay, so therefore I would have minus 1 over k natural log of g minus kv minus 1 over k natural log of g is equal to t. So in other words, t is equal to minus 1 over k natural log of g minus kv plus 1 over k natural log of g. So again, if I take out 1 over k as being common, I'm left with natural log of g minus natural log of g minus kv. And again, same log rule again. When I'm when I'm subtracting logs to the same base, I divide. Okay, so this is my equation for time when I don't know what the limits are. Okay, so what do we have to do? Well, we're looking to find, if I go back to the question, the speed as the particle tends to a limit. So if the particle is tending to a limit, that basically means that time is tending to infinity. Okay, so as time tends to infinity, what is this speed ultimately reaching? So what I need to do is get v on its own here now. So I'm going to multiply across by k first of all. So that gives me kt is equal to natural log of g over g minus kv. Now we know that natural log is the same as log to the base e, so I'm going to change this. Again, if you can't remember how to change from logs back to exponential, you go to page 21 of your maths tables, top right hand corner. Okay, and your rule there on page 21 basically states that if we have log y to the base a equals x, then that can be written as a to the x equals y. So really important to be able to change from logs to exponentials and back and forth again, okay? So what is this going to become then? So this is basically going to become g over g minus kv is equal to e to the power of kt. Okay, so I'm going to multiply everything across there by g minus kv, or actually even just flip it. So if I flip that, I have g minus kv over g is equal to 1 over e to the kt. So I can multiply across then by g, and then I can get kv on its own, and then divide across everything by k. So in other words, if I divide everything across by k, it's the same as saying 1 over k. And I can see g is common, so I'm going to take out the g as being common, which leaves me with 1 minus 1 over e to the kt. Okay, so what are we saying v is tending towards? So the time is going to tend towards infinity. Then what happens is if time tends towards infinity, there's only one part of my equation here that has time in it. And what that basically tells me is that if t is going to infinity, then 1 over e to the kt must be tending towards what? Well, it must be tending towards 0, because as t gets infinitely large, the denominator is going to get infinitely large. And if the denominator gets infinitely large, then 1 over an extremely large number or an infinitely large number is getting closer and closer to 0. In other words, it's tending to 0. So therefore, what does that imply then for our equation for velocity? Well, if all of 1 over k to the power of t is going to 0, that leaves me with 1 minus 0, which means that the velocity has to be tending towards what's left, g over k. And if we go back to the question, that's exactly what it wanted us to show. So nice, good maths, good juicy question, that one.